All right, this is section 2 of solving the exam problem. That is for exam 1 of che205. All right, so in the first section we covered part A and B. In this section we're going to cover part C. I showed you how to calculate the derivative of f of t in the previous video, which you could easily look into using a simple search in Google. So I show you one more time. Derivative of a raised to the power of a function, let's say g of x, is going to be log of a, log of the base, times a raised to the power, as before, and then times the derivative of the exponent, or the derivative of the power. This is very similar to exponential of gx. So remember, exponential of gx is g prime times exponential of gx. It's similar to now a raised to the power of gx instead of e. The only difference is you have a log a up front. Okay, so that's what we did in the spreadsheet here. So the derivative of f is going to be z1 divided by k1 squared, derivative of k1 with respect to t. So up to here is basically chain rule. The derivative of k1 is derivative of p1 with respect to t, and then derivative of p1 with respect to t is calculated from the Google search that I showed you. Okay, so at the end of the day, the derivative is going to be z1 over k1 squared as before. This is the derivative of the exponent. This is log of 10, and then this is the original function pi. Division by p is there because p is independent of the t. It's a multiplicative constant independent of t, so it doesn't change, it stays there. You notice that pi over p is ki, and you can simplify, or this is actually supposed to be p1. So I'm just getting the derivative over only the first term. The other terms will be identical. So these all need to be k1, b1, c1, a1, right? Okay, so p1 divided by p is k1. You can simplify it by this k1. So down the road you get z1 over k1 squared. And this is again k1, so times k1. And then times the derivative of the exponent times log 10. You can simplify this with k1. You get z1 over k1 now times the derivative of the exponent, which is this, times log 10. And by definition, z1 over k1 is u1. So the derivative is actually fairly simple. Is u1, the way we calculated u1 before. Remember, u1 is z1 over k1. And then times the derivative of the exponent with respect to t, times log of 10. So we're going to implement the same thing here in the spreadsheet, if you remember. So we copy this line, or maybe this line. You can copy this exactly to here, right? So let me erase this space. Right. So k1 through u4 is calculated basically, or copy paste from section B, or part B. Now we're going to calculate w1, which is the derivative of, so w1 is derivative of z1 over k1, which I just calculated in the equation right here, and that's going to be u1 times b1 over c1 times plus t raised to second power. So these all should be subindex 1, like so. Alright, so let's look at w1 one more time. So I'm going to move this right to the half of the page so you could see the equation right here and my calculation here. So let's look at w1. w1 is, look at that, it's u1, right, times b1 divided by c1 plus temperature, so here's temperature, raised to the second power, right, raised to the second power, times log 10. So one more time, u1, right, times b1, which is green cell, divided by c1 plus t, right, c1 plus t, raised to the second power, right? And then times log 10. This is it. So this is W1. You hit enter. You just drag it to the right. You get W1 to W4. Temperature, we don't change. FT we calculated before. All we need is the F prime, which is sum of W1 to W4, because derivative of this is the W1, derivative of this is W2, and so forth. Derivative of 1 is 0. So derivative of F basically is just sum of the W's. And that's what we have here. See, it's the sum of the W's. There we go. So in Newton method, the next t will be equal to the previous t minus ft divided by f prime of t. This is it. So all we do next is highlight this row completely up to here, drag one row down, highlight these two, drag one row down, then highlight the whole row, and drag all the way down. So the root is where f of t is almost 0, and you see that it's going down to 0. If you think of 10 to the minus 6 is almost 0, then this is going to be the root. So I'm going to highlight this and make it green, so we know where the root is. And you see the quadratic decrease of f. So f in every row, if you go from top to bottom, where it gets close to the 0, every time in every row actually, the f goes down quadratically, means the error. So basically this is going to be the error, because f of t is supposed to be 0, so whatever it's not 0 is going to be the error, right? So if the error right now is, let's say, 10 to the minus 1, right, almost 10 to the minus 1, then the next iteration would be this thing raised to the second power. That's what I mean by quadratically. So the error goes down quadratically, right? So this one raised to the second power is going to be 10 minus 2. If you forget about the constant number, or the number which is always less than 10, and stick to the exponent or the power of 10, you see that from here to here looks like we raised to the second power, right? So this is raised to the second power, you get 10 to the minus 2. We raise this to the second power, almost get there, that's 10 to the minus 4, let's say 10 minus, this is very close to 10 minus 4, because this is 1 10 times 10 minus 3, right? You can say almost close to minus 4, and then this thing raised to the second power is 10 to the minus 6. Okay, so you can even extend the calculation beyond what I showed. Now I actually drag it down a bit further, and you see that the error actually goes really down quadratically. So after 10 to the minus 6, you get 10 to the minus 13, which is this thing raised to the second power. And then after that, we should be 10 to the minus 26, which cannot be shown by Excel, and that is almost 0. Okay, and if you see that the root is almost fixed after, I believe, 2, 4, 6, 7 steps. 2, 4, 6, maybe 6 steps or 7 steps. So that's going to be the root and matches our part B solution, which is 326.33 up to 2 decimal digits. Okay, the third decimal digit is different because Golsek actually stops at the error of 10 to the minus 4, but Newton method actually can even go further down. Okay, so I'm going to show you that even if you make small mistakes in the derivative, Newton method still converges. So let's go back to our calculation and look at the W. Remember, the W had this log 10 constant, so I'm going to remove it, and assuming that a student made a mistake and didn't put this log 10 here. The student actually made mistakes in W2 as well as W3. So let's say in these three, the student didn't put log 10. Only W4 is correct. The other W1 to W3, these are wrong. Okay, but the mistake is just the constant we're missing, this log 10. So I'm going to show you that still Newton method converges. So I'm going to highlight this row, which has the error in the first 3 columns, and double click on this lower right corner. So it's going to calculate the rest of it, or basically it's going to populate the equations throughout. Now you see that the error doesn't go down quadratically. From 10 to the minus 2, you go 10 minus 3, 10 minus 3. So you see that in every row is not the second power of the previous row, right? This is 10 to the minus 3, 10 to the minus 4. So it goes down very slowly. It's not like before we were like getting 10 minus 2, and then minus 3, then minus 6, and then minus 13. Remember that? But this time you don't see that quadratic decrease. That's okay. So this still goes down slowly, and you get the root at the end of the day, which is again 326.33, if you think of 2 decimal digits. So if you make small mistakes in Newton's method, still converges and you get the right solution. Now imagine you forget log 10 in all terms. So I'm going to remove log 10 even from W4. So now all of the W's do not have log 10. So I'm going to highlight them and calculate the rest of it. Now this time, you see that the f of t doesn't go to 0. So it starts from 10 minus 2 and then goes back up, 10 minus 1, is all 10 minus 1, and doesn't go down anymore. And you see that even the sign of it fluctuates, so from minus, plus, minus, plus, minus, plus. So it looks like there is no monotonic decrease. So this is called like a big mistake in the derivative. If you forget all log 10 from all of them, then it doesn't converge. But if you forget just from the 3 terms out of 4, you still converge. Well, that is a specific mistake. You can even implement the different mistakes and see if Newton method converges. So my point is, small mistakes in derivatives still make the Newton method converge. However, if the mistake is large, or the error in the derivative is big, then the method doesn't converge. Alright? So, just to remind you, that was the exercise, I think, 1.10 of the textbook. We'll go back to end of the chapter textbook. So let me go back and show you one more time that this is part of actually the textbook exercise. So I'm going to go to end of the chapter 1 exercises. So this is end of the chapter 1. And if you go down, problem 1.10 is exactly the thing I asked you to do. So this is the equation we were trying to solve, and the problem actually asks you to do this, but using goal-seek. Part C of that problem is an additional step to just confirm that what you get from goal-seek is true. Okay, so that was a solution for exam 1 in che205. Thanks all for watching. Stay tuned for the next video on chapter 4, which is calculating the derivative of a function numerically.